Okay, hi everyone. Thank you for joining us once again. It is my pleasure to introduce Arne Thomsen today. I obviously am not pronouncing his name right, Arne, but we'll take it. Okay. So Arne is at the CCA, the Center for Computational Astrophysics, in the Flatiron Institute in New York, working with Francois Lanouche for 6 months as an intern. He's doing his PhD in Zurich. He's going back to Zurich soon, and he's going to tell us about his work, about his PhD work.
Yes, mostly the work. I have a little bonus on the CCA project at the end too, and then I heard that we have the full hour, but I should roughly talk for the first half, and then we discuss. So when we discuss all of this, I'm of course very happy to talk about the New York project too. This is just much more mature. So thanks a lot for the introduction, and thanks a lot for having me here. So simulation-based inference of cosmology from multiple maps using deep learning is the title, and there we'll go through these words here topic by topic. And I'm not entirely sure how people are familiar both with cosmology and simulation-based inference, while I'm sure that you're familiar with deep learning. But if at any point anything is unclear, please, during the presentation already, raise your hand and let me know, and we can discuss right then. We don't have to wait until the end. So again, thank you. Now, just to set the stage, I'm a member of the cosmology group in Zurich, and cosmology, most successful model we have so far is lambda CDM that has a bunch of free parameters, only 5 actually. Just to broadly set the stage, what we are doing here. So I had simulation-based inference in the title. The inference part is that we want to infer these cosmological parameters, and with the methodology we employ there, which is the innovative part, we want to improve the constraints on these parameters. So in the end, ideally, we would have slightly tighter posterior constraints for these parameters, or at least have shown that we can improve some aspects of the analysis in this way. And now, I always like to show a little animation. So within cosmology, I'm not looking at the CMB, but the large-scale structure. And nowadays, we have these amazing simulations where how the matter clumps together here is dependent on the cosmological parameters we saw on the previous slides. So when we analyze data like this, we can learn something about the parameters, and that's what we're doing. Now, just to continue to set the stage, I want to briefly introduce one of the cosmological probes that we're using here. Yeah, potentially this is very boring for you, but this is weak gravitational lensing. So the idea here is that we have some background galaxies that could look like this intrinsically, but we as the observer now in the green plane have some intermediate mass between those background galaxies and us. So in general relativity, this intermediate mass will then act as a gravitational lens. And here in the exaggerated illustration from Wikipedia, the unlensed galaxies could look something like this because of this intermediate mass. Now, in reality, this measurement is complicated by the fact that the galaxies in the background are not perfect circles like we see here, but follow some random orientations because they're ellipses or something similar and are randomly oriented with respect to us, at least the first approximation. But even in this case, we can still find correlations in the lensed galaxies that can tell us something about this intermediate mass. So in summary, we use shape measurements of a lot of background galaxies to learn something about the dark matter distribution in the universe. And now this is more from the machine learning application perspective, I always like to show this. Now, this is the signal, a map of the signal in one of our simulations that comes from the weak gravitational lensing, so effect on the previous slide. And this is the shape noise that is due to the random orientations of the galaxies. But if you look closely, you see that we have two very different color bars here. And if we put them onto the same color bar, these two maps look like this. And again, this is where the information lives, and this is just noise. And in reality, we only have access to the sum of these. So this is from the simulation. And to the eye, this looks indistinguishable from the noise, I would say. But yeah, I think it's amazing that we can find any signal in there. Just to set the stage. Now, to get more technical and talk a bit about how parameter inference is mostly done in cosmology. So, most of the time we start with a catalog of galaxies, so that have been observed. And the workhorse within cosmology is two-point functions. So specifically, the power spectrum in Fourier space or the two-point correlation function in real space. And now these black dots here would, these black dots are the observation that we have and evaluated with this summary statistic. Now, one thing that is very nice about this family of summary statistics is that we have an analytical prediction for it. So how the cosmological parameters enter, we can plot the summary statistic as a function of the cosmological parameters, and that's the color bar here. And now given the ingredients, so an observation that we condition our posterior distribution on, and an analytical prediction for how the summary statistic varies with the input parameter, we can, in the end, obtain parameter constraints. Yeah, you just need a likelihood in addition to this, and then some sampling procedure. Now, what we're doing is simulation-based inference, which I want to motivate now. So the first and most obvious motivation is the non-Gaussianity that is present in the cosmological fields we look at. So this is a slice for an n-body simulation. And this plot here on the right-hand side is a Gaussian random field. So this contains so-called non-Gaussian features. This is Gaussian only. And they share the same power spectrum. So to the summary statistic we saw on the previous slide, these two images are identical by construction. And now to the eye, it's very obvious to see that they are meaningfully different from each other. And for example, way higher peaks over here. So the two-point function, that whole class of summary statistics can't pick up the difference. So that motivates us to use a summary statistic that is more powerful than this. And now simulation-based inference is more broad and can take different shapes and forms. But what I'm showing you here specifically is our approach on the map level with a learned summary. So map level means that now our observation doesn't come as a catalog or table, but we look at it as a pixelized map. So cosmological field where a little cutout could look like this. And then that's the simulation-based part. The connection between this mock observation and the cosmological parameters isn't done on the analytical level anymore, but on the numerical level. So we have a forward model that we use to produce mocks, and I will go into more depth on all of these aspects throughout the presentation. Then the learned aspect is that we train a convolutional neural network to extract the information that these sorts of maps contain on the underlying parameters, cosmological parameters, but also astrophysical nuisance parameters that we want to constrain. And given all of these ingredients, we can derive parameter constraints And now here we wouldn't have an analytical likelihood anymore, good reason to believe that this follows a Gaussian distribution or something like that. So we learn that distribution tool. And again, more on that later. And now specifically for this project, so I should have said this at the beginning, this is my main project of the PhD that I pursue back home in Zurich, and it's still ongoing work within the dark energy survey. And for this specific project, we are looking at the probe combination of weak gravitational lensing that I've introduced earlier and galaxy clustering. Now, concretely, the motivation for this is a forecast paper, written by my predecessor and one of my supervisors, where he has applied the framework I showed on the previous slide to combine probes of weak gravitational lensing and galaxy clustering, and found that approach to be very, very powerful. And here in this plot, we see a comparison between a map level analysis in pink with this learned summary statistic and a power spectrum, so 2-point based analysis in blue for his paper. And I'm not showing the plots here, but this is for the combined probes of gravitational lensing and galaxy clustering. He also looked at this for the individual probes and found that the difference between the two was even larger for the probe combination. So in other words, the combination of probes, looking at them jointly and finding the correlations that way was greater, the cross correlations was greater than the sum of its parts. So besides the non-Gaussianity that underlies the main motivation for simulation-based inference in general, this is the concrete motivation for this project. Now, just a short summary. So on the one hand, we have handcrafted summary statistics like the 2-point function that is known to be limited to Gaussian information, which, by the way, is not a problem for cosmologists working on the CMB, because that is very Gaussian. But at late cosmological times, we have non-Gaussian structure formation. And this non-Gaussian information can in principle be learned by the summary statistic, the CNN, that we employ. And just bigger picture, the overall philosophy behind these approaches, very simplified. So I would say that for the 2-point function here, the physics really lies in the summary statistic itself and how you analytically predict it, what you throw in there, while the CNN over here doesn't know anything about the physics. So that is data-driven, and to get the physics right, the physics needs to be right within the simulation. But the CNN itself doesn't know anything about the physics. It can only be learned, and it can only be trained on simulations that are, of course, physics-driven. And then, I don't know if you're familiar with this, there are also ways to do simulation-based inference with other fixed handcrafted statistics that are not learned. And now the difference between these that I put in the middle and the 2-point function is that no analytical prediction exists for these. So one goes through the same procedure and would just, in my previous slide, replace the neural network by one of these statistics. Now, as I said, this is all part of the dark energy survey, which is a photometric survey. So we work with 4 redshift bins. And from the dark energy survey for weak lensing, we then get this catalog with the shapes and positions of around 100 million galaxies. And you see the Milky Way here, and this sort of tank-shaped footprint is the dark energy survey Y3 footprint. Now, let's go through the steps in the pipeline here in a bit more detail, and let me tell you a bit more about the forward model. So again, this is basically the simulation part in simulation-based inference. And simulation-based inference is also typically abbreviated as SPI, which you may have seen. Now, the backbone of the whole project is the simulation suite that we're using. And those are called CosmoGrid V1, and they are also publicly accessible. So if you're in cosmology and interested in using these simulations, please reach out to me. Now, yeah, here are some details on what the individual simulation runs are, but what I want to emphasize is that what we need for this kind of project, for simulation-based inference, is not one very high-quality simulation, but a large number of simulations that span a large area in parameter space. And that's what I'm showing you here. So this is a corner plot with 2D projections of the different parameter combinations. But what you're seeing is not a probability distribution, but the scatter plot of our simulations. So every point here is a simulation run. And yeah, there are two different priors we chose for those. But in total, there's 2,500 cosmologies here in this plot. And for all of them, we have 7 simulation runs with different random initial conditions. And then there's also this fiducial parameter noted by a star, where we have even more simulations. And this can be used for, so classically, this would be used to estimate a covariance matrix, for example, but we use it in a different way. But again, it's critical for this kind of work that we have simulations that span a lot of parameter space, because this will then be baked into the prior that we use in the analysis. And the scatter plot we see here basically is this connection between the cosmological parameters and our observation in the end. And yeah, at the CCA, they are not impressed by this, but for my group at Zurich, this was the biggest computational effort we've ever done. Yeah, and yeah, 750,000 GPU load hours and more than 200 terabytes of simulations went into this.
Sorry, good question. I think I missed something.
Yes.
So how do you choose those?
So this
Or
is
prior, like you choose where to do the simulation and then the prior, like.
so these are chosen according to a Sobol sequence, but it could also be Latin hypercube sampling. And yeah, so there's some weird lines like here for some physical reasons, but overall they just define a uniform prior, and their pink is a slightly tighter uniform prior. And to make sure that we sample the space, yeah, in an efficient way, it's a Sobol sequence and not directly drawn from the uniform prior.
Because at the omega V, you have them all pretty much at the upper edge of the type prior. Is there a reason for that?
You mean, so
For
here,
that, yeah, the horizontal one, like there.
yes, but do you mean these projections here or just
Yes.
this? Yeah, so that's then, yeah, for some additional restrictions in there. So you can only run the simulations for certain values of W0 and so on. So, but yeah, this is just a technical detail of how we could run the simulations. Yeah, so these are n-body simulations. So in there, we just have, as I said, it's light cones. We just have shells of dark matter particles. But I said in the beginning that the cosmological probes we're using are gravitational lensing and galaxy clustering. So now, probably in all of this work, the part that took or takes the most time is now this, taking these simulations and making mock observations of the dark energy survey that corresponds to these 2 cosmological probes out of them. So again, as an input, we have these cosmogrid simulations where we vary the cosmological parameters we saw in the previous scatter plot, and then there's some additional nuisances that are not important now. And from the survey, so the dark energy survey, we take certain things like the mass or the average number of galaxies per pixel and the redshift distribution, because the raw simulations are just light cones and it's a photometric survey, so we need to integrate the redshift bins like they were measured within DS to mock that up. And for weak lensing, and the forward model looks something like this, where this is the signal part I showed at the beginning. This is how we construct the shape noise that I also showed at the beginning. And there's this additional astrophysical nuisance called intrinsic alignment that also enters them. And the galaxy clustering maps are a bit simpler and constructed like this, but it means that from one light cone of dark matter particles in an n-body simulation, we have produced a mock for weak lensing and a mock for galaxy clustering. And yeah, these are made to resemble the real data, the dark energy survey and Y3 data, as best as we can. So yeah, this is basically, together with the simulations themselves, the forward model that we employ. Now, to give you an idea what that can look like, so we recognize this tank-shaped survey mask again, and yeah, there's some complications like these holes, and because they are based on very different physics, the weak lensing and galaxy clustering maps look a bit different, and the columns here, the 4 columns, correspond to the different redshift bins. So yeah, it's a photometric survey, as I said. And in the case of the dark energy survey, there's 4 photometric redshift bins each. Now, this is one example. So one example consists of 8 maps, basically. So it's like channels RGB for a regular image. In this case, we have 8 channels at the input. And I said that for simulation-based inference, having a large number of these is crucial. It makes things easier. So out of the simulations, we construct around 1 million of these examples in total. And yeah, here's the breakdown. There's these cosmologies, then for every cosmology, we have multiple realizations of the initial conditions. And then because we have full sky simulations, and this is just the tank, we can cut out 4 footprints from each, and so on. So we have around 15 terabytes of training data in the end. And now training data, so that leads me to the learned summary statistic. Now, what do I mean by summary statistic? Yeah, I assumed it in the beginning, but let me repeat. So first of all, by summary statistic, we just mean a mapping from the very high dimensional pixel space that you saw on the previous slide to something much lower dimensional. And in principle, this is very easy. This can be trivially done. But what makes it hard is that we want the output of this function, the summary, to be as informative on the parameters we want to infer in the end as possible. So ideally, and we never have a guarantee for this, but ideally, the summary statistic would be a sufficient statistic in a Bayesian sense, where the posterior distribution of the parameters we wish to constrain theta is equal whether we condition on the full map X or the summary of the full map. And you can imagine that this probability distribution here is a lot easier to work with, because while we have millions of pixels, in this case, the summary vector we have in the end has maybe 10 dimensions or something like this. So it's much easier to learn. And now what is learned about it is that, of course, the summary function S is parameterized as a neural network with trainable parameters. Now, when we wish to train a neural network, the question is the objective function. So what do we use here? This determines the kind of summary we have in the end. So the easiest thing one can do is to just use the mean squared error and perform direct regression of the parameters theta to be constrained. And now this works fine in most cases, has been done in cosmology a bunch of times by now, but it's known to be suboptimal. So what you train the network by doing this is to predict the mean of the posterior, but it throws away all other information in the posterior. So yeah, if your posterior isn't well characterized by the mean, this won't work very well. So that motivates this loss function called variational mutual information maximization. So I'm happy to talk a bit more about it later on, but for now, let me just say that intuitively, I think it makes sense that we would want to maximize the mutual information our summary statistic has on the cosmological parameters to be constrained. And that quantity, the mutual information in itself, is intractable, but we can, plug it into the definition with the Kalberg-Leibler divergence and then see that some entropy term is constant and the parameters we optimize and come up with this, where additionally the variational part is that we also fit some density estimator to approximate the unknown true posterior. And for both of these cases, we train the network on this grid of parameter values that we saw earlier, so this scatter plot. Now, another loss function that is motivated by information theory is structured very differently and works at the fiducial cosmology plus derivatives. And now in the literature, this is called information maximizing neural networks. It's not very precise. So the kind of information that is maximized here is the Fisher information. From the Fisher information, one can derive this expression, and under some assumptions, these two would lead to equivalent summary statistics, but in practice, there's a very, very big methodological difference between them. And this VLIM is what it's called, tends to be much nicer behaved. So this is what we choose to do in this work.
Can I ask you a quick
Yes,
question?
of course.
In the variational one, are the cues of, like, in the usual way, a family of functions that you choose the shape?
Yes, so the Q could be a normalizing flow, or a mixture of Gaussians works very well too, where an NLP just predicts the mean and variance of and weights of some Gaussians.
So you're still assuming Gaussians.
Yes, but only in this step, and a mixture of Gaussians is more complex than just one Gaussian. But in the end, we drop that assumption. So we only use the Q to learn the function S, but then we throw away the Q again. And the network architecture we apply in this project is very specialized and tailor-made for this kind of project. So first of all, with this tank footprint, we cover quite a large area of the sky. So we don't want to neglect the curvature by projecting this down to flat 2D. That's one thing we would desire. And the next is that, we have a complex survey mask with a lot of poles and so on. So for this, a graph representation where every pixel is a node in this graph, and then a certain number of neighbors are connected. It makes a lot of sense. And then we would like to use the helix pixelization of the sphere. And now all of these boxes here are ticked by the deep sphere graph convolutional neural networks that have been developed in Zurich a while ago, precisely for this kind of application. And I'm running out of time a bit, but just as a small mention, we really tried hard to make this scalable and make the training parallelizable over many GPU nodes. So right now, with all of this as a side note, with the kind of resolution we use in our analysis, we are limited by the physics, the quality of our modeling, and not by the computation. So we can easily scale the computation. And in the end, we get parameter constraints in our case by something called neural likelihood estimation. So I would say this is a subset of simulation-based inference. And concretely, the steps we go through is that first we evaluate our summary network on the whole parameter grid of forward model observations that we have. So from our forward model, we get pairs of a map and the corresponding cosmological parameters. So we can just pipe all of this through our summary network and get samples from the likelihood that way. Then we can fit a conditional normalizing flow to that likelihood. So yeah, we throw away the previous Q and can now use a more sophisticated model here, where the summary is fixed, so we're a bit more flexible and more stable. And we can then just sample the likelihood using standard MCMC and obtain posterior contours in the end. Now, here, I don't want you to focus on the details of the results, but the following story. So I said that basically by construction, if we did our job all right, this learned map level summary should be more informative than the 2-point summary. And in this plot here, that manifests itself in the fact that the orange contours are tighter than the blue contours. We have more precise constraints on the parameters. And now note that this is on a cosmogrid internal mock. So what we condition our posterior on comes from the same probability distribution that our forward model employs. And the message here is that with great constraining power comes great responsibility. So this is all fine and well on the internal data, but we really have to make sure that this generalizes to the real data too. And I would say that's the trickiest part of simulation-based inference. It goes back to what I said in the beginning. It's a very data-driven approach, and the physics is in the simulation. So we need to make sure that we got the physics right in our simulation, so the forward model. And now concretely how we test this is on external simulations. So what you see here is again posteriors conditioned on a cosmogrid internal mock, and we can influence the constraining power, the size of the contours, by varying the scales we go to. So we can smooth more and become less sensitive to small scale effects, and then the contours grow. And in this example, everything is very nicely behaved and the contours just grow, but even the contours for non-conservative scale cuts are unbiased and seem fine. But the way we test all of this and determine which scale cut we use in the end is through validation on external simulations. So for this plot, there's a single realization called cardinal, which within the dark energy survey. So this is only one simulation. We couldn't train our network on this, but because it's only one, it can be a more expensive simulation. It is harder to run. And we have to make sure before we touch the real data that we are unbiased on a more complicated simulation that we think reflects the real data better than what we have in our forward model. And what you see here is that for the smoothing scales are the same as over here. If we smooth a little, too little, then our sigma 8 posterior will be very biased. And when we smooth more and more, we recover something that is unbiased, but of course at the expense of precision. So this is exactly the game we have to play. We have to figure out, okay, which scale cuts can we use to be unbiased on a more realistic simulation. Now, this is at the heart of simulation-based inference, I would say. And the precise form of the contours doesn't matter, just the story. And before I conclude, just a brief side note on why I'm currently standing here and why I'm in the US. So as noted in the introduction, I've been at the CCA in New York for the past 6 months and worked with François Lanus there in a very unrelated, but still topically connected little side project. So I can't go into a lot of detail now, but we can happily discuss. There are these JAX, there's this JAX PM simulation. So it's a particle mesh simulator written in JAX. that we would like that at the moment only models dark matter, and we would like to add baryons to it. And we do that in the following quite simple way. So the equations of motion for dark matter look like this, where the force term is just proportional to the gravitational potential, and the gas has an additional term coming from the pressure. And now this additional term over here, can be very, very complicated in a full hydrodynamical simulation. But we want to see how far we can get by a very, very effective approach where we train a small and simple neural network to predict the pressure and then the resulting force from some inputs that are cheaply available within this particle mesh simulation. And that kind of effective model, where again this pressure term is learned, we fit to a very expensive hydrodynamical simulation, like realizations from the Camel's simulation suite that has been run at the CCA. And now the great thing about this is that the simulator is written in JAX, so it's differentiable. And we can fit this model within the ODE. So we can run the full dynamics of the simulation, starting from some initial conditions, and see how a different effective force term influences the results. So when we train this with respect to the positions in Camels, we can find an effective force term from within the simulation itself. So it's not a post-processing or something like that. It's really plugging a network into the simulator. Yes, and with that, I want to thank you again a lot for having me. Thank my collaborators in Zurich here, and thank you for listening too.
Thank you so much. Any questions?
So when you're training this, you didn't mention you're conditioning on the parameters, but you didn't mention how if you're conditioning on the noise, because I know that's very important for when you start looking at the data. Are you thinking about this in terms of the DES like data and thinking about trying to condition on that noise model?
How do you mean condition on the noise model?
So when you actually apply this tool to the real data, in the likelihood you would include some type of observational error, right? A noise model from the actual observed data.
Yes.
A lot of SPI tools you actually condition on a noise model to account for that.
So I'm not 100% sure that answers the question, but feel free to point it out then. But I left out some details of the forward model. So things like the redshift errors that are known within ES influence, right? So go into the forward model. So we draw from those priors when we make these maps, and we're not interested in constraining those specifically. And the nice thing about the simulation-based inference framework is that you automatically marginalize over them in the end. So and when this was the wrong. So back here, what's in orange are some additional nuisances that we marginalize over. And then the way we construct the shape noise, because we make some choice there, I would say we validate in the way that I described in the end. So we have a simulation that is much more expensive and we think is closer to the real data. And within DS Y3 at least, there was the strategy to try out your pipeline on these results. And if you're biased by less than 0.3 sigma, also marginalizing over the cosmic variance, then you have a green light to apply it. But so far we are working on the application to these mocks, and once that is done, then the application to the real data will be the next step. And this overall simulation-based inference approach, even with the learned summary, by now has been applied to deep lensing data a couple of times. But what has never been done before is this probe combination of deep lensing and galaxy clustering. So it's basically the SPI version of the 3x2 point analysis within DS.
Yes. So when you talk about limitation based on physics, within the subject physics adopted in the simulation, and is it not part of the limitation?
So subgrid physics is already going too far. So, yeah, the scales we have in the end, we smooth by quite a lot. So for example, for weak lensing, the main concern would be baryonic contributions to the field, because this is just an n-body simulation and not a hydrodynamical simulation. And overall there are lots of physical effects that only start to play a big role at smaller scales. And the strategy, because we can't run that kind of simulation for the number of simulations we would need, the strategy is just to smooth. So that's what I then showed at the contour level. We have a strategy to figure out how much we have to smooth, because that other simulation includes that too. But yeah, baryons are the simplest example, and yeah, we don't even have to go to a more sophisticated and subgrid one.
And then system.
So I understand the destination and the resolution is quite moderate or below, at times to increase the resolution, and how does it affect the SCI?
No, so I hope I understood this right, but that's what I show here is basically this. So the lighter contours are going to higher resolution. So we have less conservative scale cuts. And if we are not careful with that, the quality of our forward model just breaks down and we get a bias on the parameters we infer in the end. So I would say that, yeah, as physicists, ultimately, of course, we care about accuracy and not precision. And with this kind of framework, by increasing the resolution, we can increase the precision a lot. So we can get smaller and smaller error bars. But because our physics model isn't perfect, they will just be in the wrong place. So the accuracy will be bad. And then it's useless to us. So it's this balancing act. How much precision / resolution can we get while still being acceptably unbiased? I hope that answers the question.
Most about the resolution and the minimum of the minimum table that you can resolve the summations, because you're relying on exact statistics.
Yes, but we are, if we look at this map again, so we are smoothing the galaxy clustering maps by so much that we are way above the minimal halo distance that is resolved by our simulations. So we still have to, iron out the details of that, but yeah, we are smoothing a lot.
Anyone else? Okay, if not, let's thank the speaker again. Please grab lunch, and if you can please write down your name on that piece of paper, it's only for financial, to know that we do give the